Here we go. Sorry about that.
All right, thank you. So my talk is on Ramsey theory for diff sequences. And I think we probably know what Ramsey theory is, and we maybe don't know what diff sequences are. So I'll get to that in a little bit, but this is in the theme of arithmetic Ramsey theory. So one slogan you might hear about Ramsey theory is complete randomness is impossible. The idea that you have a bunch of people, every pair of them either knows each other or they don't. And you have a large enough number of people, then no matter what you do, there's going to be some large number that all know each other or all don't know each other. So that's one slogan you may have heard. The one I kind of prefer better is if you divide a whole into parts, is one of the parts guaranteed to retain some special structure? So if I have the edges of my K6, then sure, they contain some triangles. But if I split the edges into a red set and a blue set, I can say, well, one of my sets still has some triangles. So that's kind of the central question here. You have some structure that's contained in the whole. Ramsey theory question asks about it being contained in the part. And I'm going to start now. In the rest of this, we're not going to be coloring edges of graphs. We're going to be coloring integers. So I'm going to start with a big, bold claim about the integers, which is that the positive integers contain arbitrarily long arithmetic progressions. Now, is this still true if you split them up into two sets or two colors? Well, one of the colors contain an arbitrarily long, say, monochromatic arithmetic progression. Or what if there's 3 colors or 4 colors or any finite number of colors? And the answer to this is yes. So this is van der Waerden's theorem. So this, I've written it here in the finitary version. So given positive integers k and r, there exists some natural number n, such that if you color up to n, you're going to get a monochromatic arithmetic progression of length k. Or another way of saying this, if I color all the natural numbers, I'm going to get arbitrarily long monochromatic arithmetic progressions. So you see this n here. You might wonder, well, what's the smallest n that I can use to get a given number k? So this is the definition, motivates the definition of the van der Waerden number, WRK. So what's the smallest n that I need to go up to guarantee the presence of a monochromatic arithmetic progression of length k? And the content of van der Waerden's theorem is just that van der Waerden numbers exist. So how would you find this? Well, the general outline is kind of the same for lots of these Ramsey theory questions. For the lower bound, you just need to find one annoying coloring that avoids this. So is there some way to color up to WRK minus 1 in this special manner that avoids long monochromatic arithmetic progressions, and then show that if I'm going up to WRK, no matter how I do it, I can't avoid it? So let's do an example. So let's try to show that W23 is equal to 9. So that means we need to show that any 2 coloring of 1 through 9 includes a monochromatic arithmetic progression of length 3, but there's some coloring of 1 through 8 that doesn't. So for 1 through 8, just take this example. Suppose we have this red set 1, 4, 5, 8, and we have this blue set 2, 3, 6, 7, and you can manually check there's no monochromatic 3AP in either of those colors. Now, for the upper bound, you're going to show that we cannot do a similar thing with 1 through 9. And let's draw some stuff. So we have kind of 2 possibilities here. Either 4 and 6 are the same color, or 4 and 6 are different colors. So what I'm going to do is I'm just going to try my best to find a coloring that doesn't have any monochromatic 3APs, and then I'm ultimately going to be unsuccessful despite my best efforts. So first case to check is maybe 4 and 6 are the same color. So let's say they're both blue. And now I do not want to have a blue 3AP. So 4, 5, 6 is a 3AP. I can't change that, but I can at least make it not all blue by making 5 red. 4, 6, 8, don't want that all blue, so 8 is red. 2, 4, 6, don't want that to be all blue, so 2 is red. So you see, in my efforts to avoid a blue 3AP, I got stuck with 2, 5, 8 being red. That's my red 3AP. So to have any chance of avoiding monochromatic 3APs, I'm going to have to make 4 and 6 different colors. So let's say 4 is red, 6 is blue. And now, luckily for us, because of the symmetry here, without loss of generality, I can also say that 5 is blue. And now here is where we get to play Sudoku. So all the decisions I've made so far are going to leave me with at most one option for the remaining numbers. 5, 6, 7, I don't want that to be blue, so 7's red. 1, 4, 7, I don't want that to be all red, so 1 is blue. 1, 5, 9, not all blue, so 9 is red. 7, 8, 9, not all red, so 8 is blue. 2, 5, 8, not all blue, so 2 is red. And now we are stuck, because look at 3. If I make 3 blue, then 1, 3, 5 is a blue 3 AP. If I make 3 red, then 2, 3, 4 is a red 3 AP. So I tried my hardest to avoid a monochromatic 3 AP, and it was impossible. So W23 is equal to 9. So there's plenty of interesting things you can ask about van der Waerden numbers. There's this famous power tower upper bound that's almost certainly not tight, and you can try to push it down. But the rest of this talk is not going to be about van der Waerden numbers or arithmetic progressions. I'm just using that to like set the stage for what type of arithmetic Ramsay theorem we're going to make. And I'm kind of going to be 2 steps away from van der Waerden. So let me explain what I mean by that. So you could make this kind of more restrictive by saying I'm only going to consider arithmetic progressions whose difference lies in some fixed set of values. And this is a topic that I think Tom Brown and Bruce Landman and maybe some other people worked with, where you say that a set is R large if any R coloring of the positive integers contains some arithmetic progression that's monochromatic and has its difference in that fixed set. So that's like a strengthening, because van der Waerden's theorem is just that a set of all positive integers is R large for all R. But kind of a weakening of that is to say, we're still dealing with the differences being in some fixed set, but now we no longer care about the differences being the same as each other. So you strengthen it and then you weaken it. So I'm 2 steps away from van der Waerden, and I'm going to be talking about these diff sequences. So this is introduced by Bruce Landman and Aaron Robertson. We say that for a fixed set D, a D-diff sequence is an increasing sequence where all the consecutive differences are in the set D. So the point is they no longer need to be equal to each other. So this is weaker than the previous thing, but it's also stronger than the original thing in the sense that not every difference is allowed. It has to be a difference that's actually in D. So the rest of the talk will be about these. And an example, let's say that D, my set of allowed differences, is the set of powers of 2. Then this is a D-diff sequence because 11 minus 3 is the power of 2, 15 minus 11 is the power of 2, 23 minus 15 is the power of 2, 27 minus 3 is not a power of 2, but we don't care because we only care about the consecutive differences, which I'll sometimes refer to as the gaps. And here we have 5 gaps, we have 6 numbers, so we say that this is a diff sequence of length 6. So for diff sequences, when can you make an analog of a van der Waerden theorem? So when we can make a van der Waerden type theorem for R colors, we'll call that R accessible. So D is R accessible if any R coloring, or maybe I should say every R coloring of the natural numbers contains arbitrarily long monochromatic D diff sequences. Or for the finitary version, you can say it's R accessible if for every K, there's some N depending on R and K, such that every R coloring of 1 up through N contains a monochromatic D diff sequence of length K. And sometime later, we're going to investigate what the smallest such N is. But first, let's just do a few examples with whether something's R accessible or not to get comfortable with that. So here's my first example. D is the set of even numbers. And I claim that this is R accessible for any number R. And why is this? Because if we color the positive integers with a finite number of colors, then there's some color that you're using infinitely often. So within that color class, you're either going to have infinitely many evens or infinitely many odds. So I have infinitely many numbers of the same parity and the same color, and I can use them to find arbitrarily long D-diff sequences. Now, the other end of the spectrum, the set of odd numbers is not even R accessible for R equals 2. And to show this, all you need is one coloring that avoids arbitrarily long monochromatic sequences. So say that all the even numbers are red, all the odd numbers are blue, look at a color class. So a monochromatic D-diff sequence is only going to include numbers of the same parity, but your differences are supposed to be odd. So forget arbitrarily long, you can't even get a monochromatic D-diff sequence of length 2. And that's for 2 colors, but that automatically means that you're not going to be R accessible for any larger number of colors, because you can kind of take this lazy coloring. So to show it's not 3 accessible, use the first 2 colors the way you did for your 2 coloring and just don't use the 3rd color at all. Who cares? So similarly for any larger number of colors. Here's a thing we can say is that the degree of accessibility is the largest R such that D is R accessible. So we just saw that the degree of accessibility for the odd numbers was 1. So of course, the degree of accessibility is always at least 1. For the set of primes, it is not 3 accessible. And for the Fibonacci numbers, it is 2 accessible, but it's not 6 accessible. So these could be interesting problems to work on. I'll just quickly show why the primes are not 3 accessible. So
sorry, just for me, a sanity check. So this degree of accessibility could be infinite, right?
Yes,
in the case
yes,
of
for the set
numbers.
of evens, for example.
Okay. But
Yeah.
if D is finite, then I guess it's always finite.
Yes, if
Okay.
I think in my definition, I may have said D is an infinite set, but
Oh,
really,
sorry, I might have missed it. Okay.
No. You could consider it to be a finite set. It's just that then I think, of course, you're not going to have certainly wouldn't be R accessible for arbitrarily high R.
Sure.
I want to say you can. It will not be R. It would not even be 2 accessible for a finite set. So I think I just kind of ignored the case of a finite set.
Oh,
the idea
okay.
being, this is my biggest gap is 100. Color the first 101 numbers red, then the next 101 numbers blue, and alternate like this. You can do a lot within your block of 101, but then there's no way of jumping to the next block of the same color. So you're never going to get arbitrarily long. If you
Right. Makes sense. Okay.
Yeah. So, but you could for the smaller cases, you could ask, oh, what's the smallest n that I can use to get length 3? But I don't know if that would be very interesting. So I want to just quickly talk about why the primes are not 3 accessible, just because it gives us an example of a periodic coloring, and sometime later we might see some periodic colorings that are useful for bounding things. So let's, I'm going to kind of ditch the red and blue business and just say color 0, color 1, color 2. So for color 0, I'm going to do all the multiples of 9. Can people read this okay? And color 1, that's supposed to be 0 there, sorry. Color 1, it's going to be the even non-multiples of 9. Why 9? It's because it's the smallest odd composite number. And for 2, it's going to be the odd non-multiples of 9. And important thing to check here is that every number has been colored, and every number has been colored exactly once, which is true. So this is a valid coloring. Color 0, all the differences are multiples of 9. They're never prime. So you're never going to get a p-diff sequence of length longer than 1 with that color. Now look at color 1 or color 2. All the numbers have the same parity, but all the gaps are supposed to be prime. So your only hope is for all the gaps to be equal to 2. So you can start your diff sequence. You have x and x plus 2 and x plus 4. The problem is, by the time you get to the 9th number in the sequence, you're going to have encountered a multiple of 9. So this coloring shows that you cannot have, with this coloring, a monochromatic p-diff sequence of length longer than 8. And this is maybe the simplest one to write down, but there's actually a different periodic coloring that you can use to show that you can't get even length 6 with that coloring. So if you want something to play around with, try to find a periodic coloring that avoids p-diff sequences of length 6. All right. So the other thing we can do is we can talk about the analogues of the van der Waerden numbers. So if my set is R accessible, then I'm going to consider delta dkr, which is the smallest n such that any R coloring of 1 through n contains a monochromatic D-diff sequence of length k. And first example I'll give you is the set of multiples of b. Now this is going to be R accessible for every R. And where is this upper bound coming from? What I want you to think about is if I take all the numbers that are 1 mod B, all the differences between them are multiples of B, all the differences between them are dB. So essentially, if I have enough numbers that are 1 mod B, then by pigeonhole principle, I'm going to have enough that are the same color, and the numbers that are 1 mod B that are the same color form a dB diff sequence. And another example, this one's less obvious where the bound is coming from. This is due again to Landman and Robertson. They said, let's look at the set of all the odd numbers and also 2. So we saw that if you have only odd numbers, you're not even 2 accessible. But if you throw in just one even number, in this case 2, then you get that it's actually 3 accessible. And they have this quadratic upper bound. So in both of these cases, we see that delta is polynomial in K. And there's plenty of other examples out there of delta being polynomial in K. And then you might start to wonder, I mean, here it's maybe hard to start wondering any patterns just from 2 examples, but you might start to wonder from the other examples, if delta exists, does it have to be polynomial in K? And here's another example. Let's say the powers of 2, and this turns out to be 2 accessible. And we want to have delta of K as the smallest n, such that any coloring of 1 through n with 2 colors contains a monochromatic powers of 2 diff sequence of length K. And Landman and Robertson also investigated this. And they have this linear lower bound, which just comes from a periodic coloring modulo 8. And they have this exponential upper bound. And along with some of my colleagues a few years ago, we pushed the linear lower bound up to a quadratic lower bound, but still a humongous gap. And it turns out that powers of 2, why am I talking about them? It's because delta of K is not polynomial. So what I was able to prove is this lower bound here. And I want you to just ignore these terms over here. The important bit is this first part, 2 to the square root of 2K. The point being, this is exponential in root K. Still a considerable gap, of course, between the root K in my lower bound and the K in the upper bound. In practice, based on the computational data, it does seem like this lower bound is pretty close to the actual behavior. So I would kind of be inclined to conjecture that it's asymptotically tight. But here I'm just going to be talking about why this is a lower bound and the fact that that means delta is not going to be polynomial in K. So our aim is to show some coloring that enables us to show that delta grows faster than polynomial in K. And before that, though, I do want to illustrate this proof of the upper bound, because it also establishes that the set we're talking about really is 2 accessible. And if we were talking about something that's not 2 accessible, any lower bound we make is kind of meaningless if the real answer for delta of K is infinite. So for the upper bound, we know that delta of 1 is equal to 1. So let's proceed by induction. So suppose that regardless of what 2 coloring you have, I have some monochromatic D-diff sequence A1 up through AK contained in the first 2 to the K minus 1 numbers. And let's just say they're all red and AK is the biggest one. Well, I don't want AK plus 1 to be red, because then I could just tack it on to the end of my sequence and get a red diff sequence of length K plus 1. Similarly, I don't want AK plus 2 to be red. And I don't want AK plus 4 to be red. And I don't want AK plus 8 to be red. So in my efforts to avoid making this red D-diff sequence longer, there's a whole bunch of numbers that I have to color blue. AK plus 1 has to be blue. AK plus 2 has to be blue. AK plus any power of 2 has to be blue. But now, look at all these numbers that I said had to be blue. Look at the consecutive differences, 2 minus 1, 4 minus 2, 8 minus 4. They're all powers of 2. So they themselves form a blue D-diff sequence. And in this case, it's a blue D-diff sequence of length K plus 1. And the largest number in this sequence is AK plus 2 to the K, which is at most 2 to the K plus 1 minus 1. So in our efforts to avoid extending the red monochromatic D-diff sequence to length K plus 1, we forced the existence of a blue D-diff sequence of length K plus 1. So that completes the induction. So we've at least established now that the D we're talking about, the set of powers of 2, actually is 2 accessible. And now let's try to show this lower bound that's exponential in square root of k. So here I'm going to use some periodic colorings. And we're trying to avoid having a lot of gaps that are powers of 2. So first periodic coloring I'm going to give you, I'm going to have a repeating block 1, 0. So what I mean by that is I'm going to be coloring the numbers according to parity. So 1 is color 1, 2 is color 0, 3 is color 1, 4 is color 0, etc. And what's good about this? Well, as I said, we don't want a lot of gaps to be powers of 2. And by construction, x and x plus 1 are always going to be different colors. So at least we succeeded in avoiding gaps of size 1. Now, let's take a more complicated periodic coloring. So here, let's color mod 4. Let's do a repeating block of 1, 0, 0, 1. So 1 is color 1, 2 and 3 are color 0, 4 is color 1, 5 is color 1, 6 and 7 are color 0, etc. And you can see by construction, x and x plus 2 are always different colors. So we avoid gaps of size 2. But that's not really the most interesting part about this. The good thing about this coloring is that it also limits the number of gaps of size 1. So what I mean by that is if I have a monochromatic D-diff sequence with respect to this mod 4 periodic coloring, regardless of how many terms that sequence has, it is still going to have at most 1 gap of size 1. That is to say, we can bound the number of these smaller gaps by a constant that only depends on the coloring being used and not the length of the sequence. Now let's keep the table going. So here I'm going to do a mod 8 periodic coloring. And does anybody want to guess? It's maybe hard to infer just based on 2 things, but does anybody want to guess what my next repeating block is going to be? Something of length 8.
You take the block of length 4 and you copy it, but revert.
I think if this is what you mean, then the answer is yes.
That's what I mean.
Yeah, so the first half is just the previous one, but the second half is the so-called complement of the first half. And that way, by construction, we always have it that x and x plus 4 are different colors. So we avoid gaps of size 4. But the real good thing about this is that, again, it limits the number of smaller gaps. No matter how long your monochromatic sequence is going to be, you're going to have at most 1 gap of size 1 and at most 2 gaps of size 2. And we can keep this table going. So next, I could make a repeating block of size 16 by taking this previous line as my first half and then complementing that to get the second half. And similarly, I can recursively get more and more colorings. So if I have a repeating block of size 2 to the t that's recursively made in this manner, it turns out to be the first 2 to the t bits of what's known as the Thumor sequence. So I haven't said what the Thumor sequence is, but essentially it's if we keep doing this tack on the complement thing, but doing it infinitely, but we're not doing it infinitely, we're cutting it off after t iterations. And by construction, this is going to avoid gaps of size 2 to the t minus 1. So I'm going to call this coloring PT. So the first 3 rows of my table are P1, P2, P3. You see P3 avoided gaps of size 2 to the 2. In general, PT is going to avoid gaps of size 2 to the t minus 1. And again, we're limiting the number of small gaps. We're going to get at most 1 gap of size 1, at most 2 gaps of size 2, at most 3 gaps of size 4, at most 4 gaps of size 8, all the way to at most t minus 1 gaps of size 2 to the t minus 2. So the point is, gaps of size 2 to the t minus 1 do not happen in your monochromatic diff sequence. And gaps smaller than that, there's an upper bound that only depends on t, which is a parameter of the coloring, and does not depend on the length of the sequence. So we have a lower bound on the number of these, sorry, we have an upper bound on the number of these small gaps, which in turn is going to give us a lower bound on the number of large gaps. So let me erase my screen. So with PT, we say a short gap is anything less than 2 to the t minus 1, and a long gap is anything at least 2 to the t. And you notice exactly 2 to the t minus 1 doesn't fit into either of these categories, short and long, but that's because it just doesn't happen with that coloring anyway. So this lemma here just summarizes what was going on in the third column of our table, which is to say for all the sizes for m equals 0 up to t minus 2, you have at most m plus 1 instances of the gap size 2 to the m. And if I were to add these up for all the different sizes, I would get that there's at most t squared minus t over 2 short gaps. But your sequence of length k has k minus 1 gaps. So in turn, this upper bound on the number of short gaps gives us a lower bound on the number of long gaps. But if my sequence is going from A1 to AK, then AK minus A1 is just the sum of the gap sizes. So a lower bound for the sum of the gap sizes is the sum of the long gap sizes. We're just going to say the short ones are kind of noise and they're not going to matter too much. So we get this inequality here. AK minus A1 is bounded below by this product where this is the minimum size of a long gap and this is the minimum number of long gaps. So what I've shown you is we get a linear lower bound in terms of K. Well, that seems kind of underwhelming because Landman and Robertson already had a linear lower bound in terms of K, and I told you you were going to get an exponential lower bound. But this is a family of linear lower bounds. We have a different one for each value of t. So you can just pick the best value of t in terms of K, and it'll give you the exponential bound that you want. So in this case, t is about square root of 2k. I should just say one thing about this, which is that what I've shown you does not exactly give you this bound here. The construction that I've given you with these PT periodic colorings, it actually gives you like a factor, I think, square root k instead of a factor of k. So where is this extra multiplicative factor of root k coming from that I managed to put in the lower bound? Where it comes from is I tweaked the periodic colorings a little bit. So I gave you the periodic coloring PT. So for example, P2 was the mod 4 periodic coloring where the repeating block was 1001. You can get a slight upgrade if you use these 2 parameter repeating blocks instead. So I'll introduce P of T comma L. And the default I've given you, PT, you can think of that as being PT comma 0. What is P of T comma L? It's take PT and replace everything with 2 to the L copies of itself. So if I wanted to give you P22 instead of just P2, I would replace everything with 2 squared copies of itself. So the repeating block for P22 would be 1111, 0000, 0000, 1111. Does that make sense? So it does give a slight upgrade in terms of an extra root k factor, but it doesn't influence the exponent, which is maybe the more interesting part anyway. So we have some time, I think, to talk about the proof of this lemma. So this is the only thing I've kind of black boxed so far. How come we really are able to limit the number of short gaps when we're using these colorings? So just some bookkeeping. What I'm going to do is when I'm using PT, my repeating block is size 2 to the t. But what you can do is you can split the repeating block up into these subblocks of size 2 to the m plus 1. So if m is t minus 2, I only have 2 subblocks. If m is t minus 3, I have 4 subblocks, etc. And if your residue is anywhere from 1 to 2 to the m, mod 2 to the m plus 1, we'll say you're in the first half of the subblock. Otherwise, we'll say that you're in the second half of the subblock. And an important observation here is that if you look locally at a subblock, it really just looks like the whole repeating block for a different periodic coloring. Like a subblock of size 2 to the m plus 1 looks like the repeating block for pm plus 1, possibly with color 0 and 1 switched with each other. But let me just illustrate this. If I'm using, say, size 8, so p3, and I'm repeating this over and over again, and let's say m is equal to 1, so my subblocks are size 4. If you look at a block of size 4, well, 1, 0, 0, 1, that's just my repeating block for P2. And 0, 1, 1, 0 is just the same thing if I switch the roles of the two colors, and it doesn't really matter if I do that. So locally, it looks kind of like we're in a different coloring. And if you remember, with PM plus 1, by construction, I can never add 2 to the m and stay on the same color, which is to say that if I'm adding 2 to the m here within PT and staying on the same color, it means I'm switching which subblock I'm in. So if adding 2 to the m switches which subblock you're in, it means that what we're doing is we're moving from the second half of a subblock to the first half of the next subblock. So what I'm saying is, whenever your gap is of size 2 to the m, it can't happen when AI minus 1 and AI are in the same subblock. So it means AI minus 1 is in the second half of its subblock, and AI is in the first half of the next subblock. And one consequence of this is that I cannot use the same gap size twice in a row. So whenever I use gap size 2 to the m, I move from the second half to the first half. But I'm in the first half now, so I can't use another gap of size 2 to the m immediately, because all such gaps begin in the second half. And we can take this a little bit further. So you can also think about gaps that are bigger than 2 to the m. Since everything's a power of 2, the gaps that are bigger than 2 to the m are divisible by 2 to the m plus 1, and my subblocks are size 2 to the m plus 1. So if I add a multiple of 2 to the m plus 1, it doesn't change where I am within my subblock. So if I use a gap of 2 to the m to move from the second half to the first half, and then I add some bigger gaps, I'm still in the first half of whatever new subblock I'm in. So if I want to kind of reset and get back to the second half, I need to use a smaller gap at some point. So to summarize, a gap of 2 to the m takes me from the second half to the first half. A bigger gap keeps me in the first half. If I want to go back to the second half, I have to use a smaller gap. And why do I care about going back to the second half? Is because if I want to do another gap of size 2 to the m, I have to do that. So a consequence of this is between every 2 gaps of the same size, there must be at least one gap of a smaller size. Now, what that means, m is allowed to be 0. So what I'm saying is between any 2 gaps of size 1, there is a gap of a smaller size, but there is no smaller size. So that means there's at most one gap of size 1. And between every 2 gaps of size 2, there's a gap of a smaller size, but the only smaller size is size 1, and there's at most one gap of size 1. So that means that there's at most 2 gaps of size 2. Unfortunately, you have to do a little bit more work to get the full content of this theorem, because you might think, okay, can I use this to show directly that there's at most 3 gaps of size 4? And not quite, because of the following thing. So I can actually, this is not actually possible, but it's not obvious why it's impossible. If I give you this pattern of gaps of size 1, 2, and 4, and let's just ignore the fact that there might be some 8s and 16s and 32s mixed in between that don't affect you mod 8. then here it looks like, okay, this seems to be following the rules. Between any two 2s, there's a 1. And between any two 4s, there's either a 1 or a 2. It turns out something like this is not actually possible. So we'll be able to get that there's actually an upper bound of 3 4s instead of 4 4s, and there's an upper bound of 4 4s instead of 8 4s. But this basic observation that between every 2 gaps of the same size, there's a smaller size, at least starts us off. So we have most 1 of size 1, most 2 of size 2. And we're going to now proceed by induction. So up to q minus 1, I'm going to say there's at most m plus 1 gaps of size 2 to the m like we wanted. We know the base case is true. And for the sake of contradiction, I'm going to assume that there's at most q plus 2 gaps of size 2 to the q. And I'm not going to do all the computations here, but I am going to describe the general strategy that'll then get the job done once you actually do the computations. So here, we know that between consecutive gaps of size 2 to the q, there's some smaller gaps. And I don't really care about the bigger gaps because they don't affect what I am mod 2 to the q plus 1. So I'm going to say that A1 is the size of the small gaps between the first and second gaps of size 2 to the q. And A2 is the total size of the small gaps between the second and third gaps of size 2 to the q. So here's my schematic. So what I've done is this is just a snapshot of what part of the monochromatic D-diff sequence looks like. And this things that I've marked here, these are my gaps of size 2 to the q. And we know that in between, we don't have any other gaps of size 2 to the q, but in between, we know exactly what's happening mod 2 to the q plus 1. So the total sum of all the gaps from AI1 plus 1 and AI2, the total sum in here is what I'm calling A1. Well, at least it's A1 mod 2 to the q plus 1. And the sum within here of all these gaps is going to be A2 mod 2 to the q plus 1. And then let's say maybe my next gap of size exactly 2 to the q takes me from, say, AI4 to AI4 plus 1. Then this gap, the sum of all these gaps in here is going to be what I'm calling A3 mod 2 to the q plus 1. So the thing to remember is that every gap of size 2 to the q takes you from the second half mod 2 to the q plus 1 to the first half. But then when I'm adding all these small gaps in between, it's taking me back to the second half so that I'm able to do another gap of size 2 to the q. So each of these aij's, the beginning of the gap of size 2 to the q, is in the second half of its respective subblock. You add 2 to the q, you move to the first half, and then when you add the corresponding aj, you move back to the second half. So we keep switching halves. And I claim that this is going to give you some sort of lower bound on the sum of the AJs. And you might say, well, hold on, can't I switch halves without getting much of a lower bound? Because I could go from like the last one in this half to the first one in the next half. And that's a lower bound of 1. That seems pretty useless. And while it's possible that maybe one of these AJs is equal to 1, we're still able to get a substantial lower bound for the sum of them. So let me just draw this little schematic here. So let's suppose here are 3 subblocks of size 2 to the q plus 1. I'm drawing them like they're disjoint, but really the left endpoint of one of them is the right endpoint of the previous one. And I'll just draw the midline in between them. So if you move from the second half of one of these to the first half of the next one, you maybe haven't moved very far. But if I move from the second half to the first half to the second half, then you see that I've at least traversed half a subblock in between. And if I move from, say, the second half to the first half to the second half to the first half again, to the second half again, then you see that I've traversed at least 3 subblocks in between, right? Doesn't matter where I start and where I end, 3 halves of a subblock. This half, and this half, I've traversed the whole thing. So if you work out the details of this, it will provide a lower bound on the sum of the AJs. But remember, the AJs are made up of the smaller gaps. But by the induction hypothesis, we have an upper bound on the number of small gaps, at most 1 of size 1, at most 2 of size 2, at most 3 of size 4, etc. So the induction hypothesis gives us an upper bound on the sum of the AJs. But this business with having to keep switching halves gives us a lower bound on the sum of the AJs, and this gives us a contradiction. So that's the proof of the lemma. And that's the last thing that we needed to establish that we really do get this exponential lower bound for delta of k. So just a couple things you might be wondering, and kind of questions that we can ask from this point going forward are for delta of k. So the smallest number that I need to color to guarantee the presence of a monochromatic powers of 2 diff sequence with 2 colors. I have this lower bound with 2 to the square root of 2k, but I didn't really do anything to improve Landman and Robertson's upper bound that we saw with that 1-page induction argument. So it's natural to ask if you can improve the upper bound, and if so, can you push it down and actually get the correct asymptotic? But maybe powers of 2 aren't really the most interesting thing. I mean, you can ask a diff sequence question about any set D that you want, but there's maybe nothing inherently interesting about powers of 2 besides the fact that they kind of just serve as this proof of concept that you can get delta to grow faster than polynomial. So you might wonder instead, well, what are the various behaviors that are possible for delta? Like, is powers of 2 like the fastest growing thing that you could possibly get? Or is there some other D that I could pick maybe that's going to go faster than 2 to the order of root k? And if that's the case, what's the highest? If there is a highest, what's the highest growth order you can get? Is it possible to get some other set that'll grow faster than 2 to the k? So I think I maybe have 5 to 10 minutes left that I'll use to just talk about some of the other results I have that are a little different from this. So this is going back to when we talked about the degree of accessibility. So it's like, what number of colors prevents you from making a van der Waerden theorem? And for powers of t other than 2, you might wonder why I've only talked about powers of 2. Well, for powers of t other than 2, it's not even 2 accessible. And the reason for this is because powers of t are all congruent to 1 mod t minus 1. Now that's true for powers of 2 as well, but it's also meaningless for powers of 2. But for anything else, what we can do is we can take a periodic coloring mod t minus 1. So for example, let's just say I'm looking at the powers of 4. I'm going to do a periodic coloring mod 3. So maybe what I'll do is everything that's a multiple of 3 will get color 0. Everything else will get color 1. So my coloring looks like this: 1, 1, 0, 1, 1, 0, 1, 1, 0. And whenever I'm adding a multiple of 4, what I'm doing is I'm moving up 1 mod 3. So within 3 steps, I've hit a multiple of 3. I've hit color 0. And if I start at color 0, I can't do anything without hitting a number that's going to be colored 1. So similarly, you can do something like this mod t minus 1 to avoid arbitrarily long sequences where the gaps are all powers of t. So let's maybe look at something more general and say, just look at any set where each term divides the next one. And a different way of parameterizing this is to say, start with some sequence, say A1, A2, etc., and let D1 equal A1, D2 equal A1 times A2, D3 equal A1 times A2 times A3, etc. And I'm going to use that to make this set that I call DAN. Now, we know that DAN is sometimes 2 accessible because the powers of 2 is such a DAN. It's DAN when A1 is equal to 1 and everything else is equal to 2. So you might wonder, well, when is this going to be 2 accessible? And it turns out it's 2 accessible if and only if the underlying sequence AN contains arbitrarily long strings of consecutive 2s. So one fun consequence of this is that the set of factorials, which is what you get when A1 equals 1, A2 equals 2, A3 equals 3, etc., the set of factorials is not 2 accessible. And to prove this, what I did is I wanted to generalize this notion of the periodic coloring that we use for powers of t. But how I interpreted a generalized periodic coloring was in terms of BD sequences. So the idea that this periodic coloring, say mod 3, what it really is you're coloring the numbers based on, I believe, the parity of 2/3 times n. So if we want to color the numbers based on the parity of the floor of alpha times n, if alpha is rational, you get a periodic coloring. But if alpha is irrational, you get this kind of pseudo periodic coloring. And it turns out that for any of these DANs, which is not too accessible, there's some choice of alpha that you can pick such that this coloring according to the parity of floor alpha n is enough to avoid arbitrarily long DAN diff sequences. And just one example of that. This is the only one where I explicitly constructed alpha. The others I just kind of showed by some process that it has to exist. So for the set of factorials, if you take alpha equals 2 minus e over 2 minus 1 over 2e, you get this explicit, say, pseudo-periodic coloring that avoids factorials, diff sequences of length 4. And the fact that e shows up is maybe not too surprising, because if you write out the Taylor expansion, it's going to be in terms of factorial. So there's kind of that immediate connection there. So a couple other questions this got me thinking about is like, what other sets might not be too accessible? So we know from before the powers of t are not going to be too accessible if t is bigger than 3, but it's only happening for these modular arithmetic reasons, which you can kind of think of as a local obstruction. So I kind of wanted to know about, are there other things that are not too accessible instead because of sparsity reasons? So I thought, well, what's something that I can make that's exponential but doesn't have to worry about modular arithmetic? So I decided maybe the natural generalization is to take the sequence, you fix some alpha, fix some delta, and take your set to consist of the floor of alpha delta to the I for all I. You also could do like the ceiling of alpha delta to the I. So one kind of nice thing about this is if you look at like Binet's formula for Fibonacci numbers, the Fibonacci numbers are in this d alpha delta form with delta equals 1 plus root 5 over 2. And that's something that is too accessible. So if I had to guess, I would guess that we're going to be too accessible when delta is in the interval from 1 to 2, and we're not going to be too accessible when delta is bigger than 2. And that's consistent with the examples I know about, but I also don't know a whole lot of examples, so I can't really say. And then if you're willing to sacrifice some of this regular structure and you just want to ask, well, how fast can something grow and still be too accessible? Obviously, we talked about powers of 2, I can double every time and still be too accessible. So what I'm curious about is there some set where each one is more than twice the previous one, but it still ends up being too accessible? So kind of the two main types of questions I have going forward are, if you are accessible, what kind of function can delta dkr be? And what my other main theme of questions is, well, what kind of sets are growing, say, too fast to even be accessible? All right. So thank you for coming to my talk. I'm happy to take any questions.
All right. Thank you very much for the talk. Are there any questions? So I have one, and I mean, it might be very easy or very hard, and I can't decide which one it is, but what if we choose D randomly in some sense? So for every integer, we flip a coin, and with probability P, this coin shows heads, and if it shows heads, then we put it in D and otherwise not. Will this be too accessible in general?
That's a really interesting question. My basic, I will say I haven't worked on something like this at all. I think my basic instinct would be yes, because there's this Landman Robertson example here. Okay, so this was 3 accessible, not 2 accessible, with the idea that just adding one even number took you from not even being 2 accessible to being 3 accessible. And now I'm not sure if any even number gets the job done. Maybe specifically you had to add 2. But the idea that the big limitation so far
Mm.
seems to be these modular arithmetic issues. So if you're doing this randomly, I think you're going to have probability 0 of getting such a modular arithmetic issue.
Yeah.
So I'm inclined to
probably.
think that you would be accessible. And the other end of the spectrum, I don't know if sparsity issues are a problem or not, but you're also going to have probability 0 of getting these sparsity issues.
Mhm.
So I'd be inclined to
So
think,
kind of all the problems that you know will not show up, I guess.
yeah, I'd be inclined to think that if you have a positive probability of picking any given number, then you're going to have probability 1 of being at the very least 2 accessible, but that's just a guess.
Okay.
And then I wonder also maybe if you want to still go in this probabilistic direction, but give yourself a higher chance of failing, if you could change the probability based on what the number is. So I don't know, say you have a 1 over p chance of adding p to your set, if that could cause any issues. I don't know.
Sure.
But that's kind of that's a cool idea. I didn't think about that.
Oh. Thanks. Any other questions? That doesn't seem to be the case. So thank you again, Alexander, for the talk.